The dataset used in this project was obtained from the number of active government mobile applications on data.gov.my. For the purpose of this study, we extract 10 data points specifically from two variables, which are dates in months from January 2025 until October 2025 and number of active government mobile applications. The analysis used both manual calculations and Maple software to obtain the best quadratic, fit curve, error vector and magnitude of error vector. These are the data that we specifically selected from the source.
In this part, I will explain the manual calculation part for fitting the data using a quadratic model. First, we are given the values of x from 1 until 10, together with their corresponding y values in the table. In this case, we use x as number of months in 2025, and y is number of active government mobile application. Since the pattern of the data is slightly curved and not perfectly linear, we use the quadratic model, which is y equal to a plus bx plus cx squared. Next, each value of x and y is substituted into the equation. After that, all equations are written in matrix form as ax equals b, where matrix A contains the value of a, bx, and cx squared. The vector x represents the unknown a, b, and c, while vector b contains the original y values. Since the system has more equations than unknowns, we apply the least squares method by forming the normal equation, which is A transpose AX equal to A transpose B. First, we find A transpose A. We got 3 by 3 matrix, and then we need to find A transpose B, and we got 3 by 1 matrix. Then we perform matrix equations and do Gaussian elimination. Therefore, we got A equal to 433.3008, B equal to 6.2530, and C equal to negative 0.0985. Lastly, the final quadratic equation obtained is y equal to 433.3008 plus 6.2530x minus 0.0985 x squared.
In this part, we will calculate the error vector, which we call SE. To find this vector, we use formula E equal to B minus AX. First, we need to multiply matrix A by vector X, then subtract it from the actual data vector B. We now obtain the error of each individual row. Next, we want to find the magnitude error. The magnitude error is calculated as the square root of the sum of the squared error. Substitute the value into the formula and we have the magnitude error of 6.7010.
Next, I'm going to present about our calculation using Maple software. Our data consists of 10 months of records where the independent variable x is the month number and the dependent variable y is the number of active apps. To do this analysis, we use Maple's package, which is linear algebra and plots to handle our math and graphs. Firstly, we plot our data points. We started by setting up our input vector x for months 1 through 10 and our output vector y for the application counts. To see the trend, we made a scatter plot using the point plot command. As you can see in the graph, the data points show a clear upward trend with a slight curve rather than a perfectly straight line. The graph of scatter plot above indicates the relationship between month number, which is x, and number of government, which is y. Next up is least square solution. To set this up as a linear system, we constructed a design matrix A. Each row of matrix A corresponds to our quadratic parameters, containing A1 for the constant term, the value of x for the linear term, and x squared for the quadratic term. We then created an augmented matrix, which is A and vector y, and computed its reduced row echelon form to see if an exact algebraic solution existed. As you can see from the output, the first row reduces to the equation 0 equals to 1. Since 0 equals to 1 is a false statement, it proves that our system is inconsistent and has no exact solution. Since augmented matrix has no exact solution, therefore, we obtain the best quadratic solution by using normal system. The equation of normal system is A transpose A X equals to A transpose B. Firstly, we need to compute determinant A by calculating A transpose and A transpose A, which resulted in 435,600. Since determinant A does not equal to 0, the metric has unique solution. Therefore, we solve the system by using Gauss-Jordan elimination. To perform Gauss-Jordan elimination, we multiplied A transpose by our target vector, which is Y, to find our right-hand side vector, which is A transpose Y. We combine this into a new augmented matrix, which is A transpose A and A transpose B, and apply by Gauss-Jordan elimination via the reduced row echelon form command. And then the final column of this reduced matrix directly hand us our optimal coefficient, which our constant A is 4,333 over 10. Then our linear coefficient B is 4,127 over 660. And then our quadratic coefficient C is negative 13 over 132. Next, we substitute our value back into our model, which gives us the best fitting quadratic equation. And then, we visualize the curve fit by using a plot command to get a quadratic curve, which is the parabolic curve passes through the center of our scatter point. The graph shows the best fitting quadratic curve.
Lastly, to find the error, we just use the error formula, which is B minus A of X. And to find the magnitude of error, we just use the norm command, error2, to find the answer. Using both manual calculations and Maple software, the best quadratic fit curve is Y equals to 433.3008 plus 6.2530x minus 0.0985x squared. A key indicator of the model's accuracy is the magnitude of the error vector, which is 6.7010. Although the model is not perfect, the amount of error is still reasonable for a small dataset. The quadratic curve is useful for describing the pattern of numbers of active government mobile applications every month.
Thank you.